Hello, I'm Hayden McTavish, and I'm here to tell you about how to build better interpretable models in the presence of missing data. This work is all about a powerful and simple class of models: interpretable, sparse, generalized additive models. The models look like this one: a handful of shape functions, each of which maps from a feature value to a score with just a few stair-step jumps. To evaluate the score for a sample, we map each feature to its corresponding shape function. We're just evaluating a small number of univariate functions and summing them. But what happens if there is missing data? Suddenly, it's not so clear how to evaluate this function. If we follow standard statistical practice and impute the missing data, suddenly it's really hard to communicate the map from the data we know to the prediction. Unless we're doing very simple imputation, the shape function becomes multivariate. This is really bad because if we try to represent the map from known data to predictions as a single interpretable model, the interpretability of our model class collapses. Instead, we present a model which adjusts its parameters in the presence of missingness. The model on the bottom uses the faded lines to match the original model when data is not missing, but adjusts with the green lines when data is missing. So how do we find these awesome models? Say we have a dataset with missing values. We can start by simple zero-value imputation when a value is missing. We can train a GAM on this data without missing data handling to get a basic shape function, which will be great to use when data isn't missing. Then we can do missingness indicator augmentation to allow some simple adjustments to our score function when a value is missing. Lastly, we add interaction terms between missingness and other feature values, allowing other shape functions to compensate when we can't get information out of some missing feature. This does create an explosion of possible terms, but because we're leveraging some very clever optimization to find sparse solutions, the models remain simple to express and tractable to compute. To evaluate MGAM's interpretability and accuracy, we compare it with a number of baselines for generalized additive models with missing data. We evaluate the model's accuracy and its sparsity, in this case the number of non-zero coefficients, each of which is a stair-step in the shape functions we were showing earlier. Notice that MGAM produces models that are significantly sparser than other methods. That is, they have fewer non-zero coefficients. Additionally, it produces higher test accuracy. As an aside, we have multiple points for MGAM rather than a single point, because the optimization method we use provides a range of model options with increasing numbers of coefficients, corresponding to different levels of regularization used. Users run the method just once and are given a range of model options depending on their desired sparsity. Not only can we perform well on real data, but we can arbitrarily outperform imputation or just missingness indicators when we're using the interaction terms that we have in this model. Here we show our method's performance on a couple of real-world datasets with some additional synthetic missing at random missingness. This is the kind of missingness that's normally used with imputation, but because this is a predictive task, it turns out that using a standard imputation approach is arbitrarily worse than if we allow interactions on our MGAM model. These interactions are also arbitrarily better than if we only allow missingness indicators on our MGAM model. If you'll recall, the interactions are when we allow other shape functions to adjust to compensate when one feature is missing. If you'd started a computation at the beginning of this talk for missing data, then our method would be done by now. Some trivial imputation methods that are much less accurate, like mean value imputation, would be done too technically, but you probably wouldn't find them very helpful. Meanwhile, state-of-the-art multiple imputation methods would not be done. Thank you for listening to our talk on interpretability via augmented generalized additive models. For GAMs, standard approaches for missing data reduce interpretability. So we introduce a GAM approach for missing data, which beats competitors on sparsity and accuracy, can model missingness patterns not covered by missingness indicators or imputation, and requires less runtime than multiple imputation to complete. Please check out our paper for further details, and thank you again for listening to our talk.